Hello, in this lecture we'll answer two questions. In the first question we will find out the length of line segment X that is equal to DE, and in the second question we will find out the value of the shaded area that is inside this quarter circle. Okay, we'll start with the first question. In the drawing we have triangle ABC. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. And this angle BAE equals to 60 degrees. Line segment BD equals to 5 units. Line segment CE equals to 4 units. And our mission is to find out the length of line segment DE that is equal to X. Okay, so first of all we will focus on triangle ABC. In triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees, therefore they are equal to each other. So I write it down. So this angle, that is angle ABC, is equal to this angle, that is angle ACB. Both angles are equal to 30 degrees, therefore they are equal to each other. Okay, I'll repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles are equal to 40 degrees, therefore they are equal to each other. Okay, so, and we have the rule that in front of equal angles in the triangle, there are equal sides. So here in front of this angle we have side AB, in front of this angle we have side AC, and those two sides must be equal to each other because they are located in front of equal angles. So here we can write down that side AB equals to side AC. Okay, according to the one that I mentioned, side AB must be equal to side AC. In addition, we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So we will define angle EAC as alpha. We will define angle BAD as beta. And we know that the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees. This angle is also equal to 30 degrees, plus this angle that is equal to alpha according to our definition, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those all angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So I repeat again, the sum of the angles, this equation states that the sum of the angles in triangle ABC equals to 180 degrees. Okay. So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. And we also have here on this side of the equation plus alpha plus beta. And the other side of the equation we have 180 degrees. It equals to 180 degrees. So we subtract 120 degrees from this equation. And we get that alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. So we found out that alpha plus beta equals to 60 degrees. In the next step, we will do two constructions. From point A, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal. Actually here I will change it to I will change this angle as angle. So we will draw a straight line in such a way from point A that the angle that we created, the angle between the straight line and side AC will be equal to beta. So actually this angle equals to beta according to our construction. And the second construction that we will do is from point C, we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. I'll repeat again that this angle will be equal to 30 degrees according to our construction. In the next step, we will extend the two straight lines until they intersect with each other. And we'll define the intersection point between the two straight lines as point F. Point F is the intersection point between those two straight lines. Actually, we created here a triangle AFC. In the next step, we'll prove that this triangle, triangle AFC, is congruent to this triangle, triangle ABD. So we'll prove that this triangle, triangle ABD, is congruent to this triangle, triangle AFC. So why those two triangles can go into each other? First of all, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle, angle BAD, equals to this angle that is actually angle CAF. Those two angles are both equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF, they are both equal to 30 degrees, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. So side AB in triangle ABD is equal to side AC in triangle AFC. Okay, AB equals to AC according to what we have already found out. Okay, and finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle, angle ABD in triangle ABD, is equal to this angle that is actually angle ACF in triangle AFC. They are both equal to 30 degrees, therefore they are equal to each other. I repeat again, angle ABD equals to angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So actually, we proved that this triangle, triangle ABD, is congruent. This is the sign of congruent to triangle AFC according to angle side angle rule. Okay, triangle ABD congruent to triangle AFC according to angle side angle rule. I'll explain what I mean. Actually, we proved that those two angles that are 30 degrees and beta and the side that attached to those two angles, that is side AB in triangle ABD, this triangle are correspondingly congruent to those two angles that are actually beta and 30 degrees and the side that attached to those two angles, that is side AC in triangle AFC. Therefore, we proved that those two triangles can go into each other according to angle side angle rules. We have two angles and the side that attached to those two angles in triangle ABD that correspondingly congruent to those two angles and the side that attached to those two angles in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude is that side BD equals to side FC. Side BD equals to side FC. I'll repeat again. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. Okay? But it is given us in the question that side BD equals to 5 units. So we can write here that BD equals to 5, and from this equation 5 equals to BD equals to FC, we will derive that FC is also equals to 5 units. Okay, so here side FC also equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD equals to side AF. According to the same rule that corresponding sides in congruent triangles are equal to each other. And if we define side AD as A, here AD equals to A according to our definition, so we can write here that AD equals to A, then from this equation we will derive that side AF is also equals to A. And side AF equals to A. Okay, you can write down here that side AF is also equals to A. In the next step, we will join points E and F together by a straight line. And we will prove that the green triangle ADE, is congruent to the orange triangle AEF. This triangle. Okay, but before that, we actually we already found out that alpha plus beta equals to 60 degrees. Therefore, we can write down that this angle EAF, that is equal to alpha plus beta, it is equal to 60 degrees according to what we have already found out. Okay. Now we will prove that the green triangle is congruent to the orange triangle. The green triangle is triangle ADE, and is congruent to the orange triangle that is actually triangle AEF. So why those two triangles congruent to each other? First of all, we just right now proved that those two sides are equal to each other. They are both equal to A, therefore they are equal to each other. So side AD in the green triangle is equal to side AF in the orange triangle. They are both equal to A, therefore they are equal to each other. I'll repeat again. Side AD equals in the green triangle equals to side AF in the orange triangle. They are both equal to A, therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. Okay? So angle DAE in the green triangle is equal to angle EAF in the orange triangle, and both angles are equal to 60 degrees, therefore they are equal to each other. So angle DAE in the green triangle is equal to angle EAF in the orange triangle. They are both equal to 60 degrees, therefore they are equal to each other. And finally, we have side AE, that is a common side that belongs to both triangles, so side AE equals to itself. AE equals to AE. It's a common side that belongs to both triangles. I'll repeat again. Side AE equals to side AE. It is a common side that belongs to both triangles. Therefore, we actually proved that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF, according to side angle side rule. The green triangle, triangle ADE, congruent to the orange triangle, triangle AEF, according to side angle side rule. I'll explain what I mean. Here, those two sides and the angle that is included between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between them in the orange triangle. So therefore, those two triangles can go into each other according to side angle side rule. We have two sides and the angle that is between them in the green triangle that are corresponding congruent to two sides and the angle that is included between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side EF. Okay. We conclude that side DE equals to side EF. Side DE equals to side EF according to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given us in the question, side DE equals to x. So I can write here that DE equals to x. And from this equation, x equals to DE equals to EF, we will derive that side EF is also equals to x. Side EF is also equals to x, so I can write here that EF equals to x. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. So, what is the law of cosines? Actually, the law of cosines, I already mentioned it a couple of times before. The law of cosines is true in any triangle. So I can write here that in any triangle, So actually, if you have here triangle ABC, that could be any triangle. This is triangle ABC. We know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. And we also know that side BC equals to C units in its length. Then the following equation is true in this triangle, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I repeat again, in this triangle ABC that could be any triangle, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines, this law, in triangle EFC. So I will copy triangle EFC in a new page, in this page, and we will implement the law of cosines in this triangle EFC. Angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units. Side EC equals to 4 units. And side EF equals to X. So this is triangle EFC that I copied from the original drawing. So according to the law of cosines, this triangle EFC, we will get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again, according to the law of cosines in this triangle EFC, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. This equation is the implementation of the law of cosines in this triangle EFC. So we actually found out that x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees is 1/2, so we substitute cosine 60 degrees by 1/2. So in total this expression equals to minus 40 times 1/2. So here we found out that x squared equals to 16 plus 25 is 41, and here we have minus 40 over 2 is minus 20. So here we found out that x squared equals to 41 minus 20. So x squared equals to 41 minus 20, that is 21. So here we take a root out of this equation, and we get that the value of x equals to either to the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, actually this is the answer to the question, and the reason that x equals to the positive root of 31 and not to the negative square root is because of the fact that x is a length, and as a length it must be a positive number. So the answer to the question is that here line segment DE that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, so actually finished with the first question. In the next step I will present to you the second question. So here in the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at this point. We know that the radii of the circle and the semicircle, they are both equal to 2 units, and we also know that this circle is tangent to the quarter circle at this point, and our mission is to find out the value of this shaded area. Okay, so first of all, because of the fact that this is a quarter circle, then this point must be the center of the quarter circle, so we'll define this point as point O, and point O is the center of the quarter circle, point O is the center of the quarter circle, and this angle equals to 90 degrees. This angle must be equal to 90 degrees. It is true in any quarter circle. We'll define this point as point A. We'll define this point as point B. And in any quarter circle, line segment BO and line segment OA are defined as the radii of the quarter circle. Therefore, here we can write down that line segment BO is the radius of the quarter circle. We'll define the radius of the quarter circle as capital R. Therefore, line segment BO equals to capital R. Likewise, line segment OA will be also equal to capital R, that is the radius of the quarter circle. But here from the drawing, you can see that OA, that is also a tangent to this circle at this point. OA is tangent to this circle at this point. So we'll define the point of tendency of tangent OA with this circle as point M. I write it here. Point M is the point of tangency of tangent OA with this circle. We will define the center of this circle as point P. We define the center of this semicircle as point Q. Point P is the center of the semicircle. Point M is the point on the point P is the center of this circle. Point M is the point on the circle itself. That is to say, PM is the radius of this circle that is equal to 2 units according to what is given us in the question. Okay? So PM is the radius of this circle, and we also have that is equal to 2 units. And we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here tangent AB, this tangent AB is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we also we have the radius OM that is drawn to the point of tendency. That is to say, the radius OM, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. Again, if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also will be equal to 90 degrees according to this rule, number 1. So we can implement actually all this rule number 1 in our drawing. Why? Because in our drawing we have the radius PM that is drawn to the point of tendency. That is to say, the radius PM, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1. Okay? In the next step, from the center of this circle that is actually point P, we draw perpendicular on QO. Okay? So this angle equals to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction also. And we define the touching point of the perpendicular from point P and QO as L. L is the touching point between the perpendicular from point E and QO. Actually, by this construction, we created quadrilateral LPOM that has 1, 2, 3 right angles. Repeat again. By doing this construction, we created here quadrilateral LPOM that has 1, 2, 3 right angles. So I write it down. This quadrilateral LPOM has 1, 2, 3 right angles, and the sum of three right angles is equal to 90 times 3. 90 degrees times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LPM, In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtract 230 degrees from this equation, and we will get that the missing angle, that is actually angle LPM, is equal to 360 degrees minus 270 degrees. It is equal to 90 degrees. Okay? So if we found out that the missing angle is a right angle, it is equal to 90 degrees. This angle equals to 90 degrees. Therefore, in quadrilateral LPOM, we have four right angles. And any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM as a rectangle. Okay? Quadrilateral LPOM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle LPOM must be equal to each other. That is to say, PM must be equal to LO. PM equals to LO, according to the rule that the opposite sides of a rectangle are equal to each other. Here PM equals to LO. But we know that PM is the radius of the circle that is equal to 2 units. So I can write here that PM equals to 2. And from this equation, 2 equals to PM equals to LO, we derive that LO equals also to 2 units. Here, LO is also equals to 2 units, according to the same rule that the opposite sides of a rectangle are equal to each other. We will conclude that side LP equals to side OM. If side LP equals to side OM. Side LP equals to side OM. Side LP equals to side OM, according to the rule that the opposite sides of a rectangle are equal to each other. And if we define side LP as x, here side LP equals to x according to our definition. Here side LP equals to x. Then from this equation, x equals to LP equals to OM, we will derive that side OM is also equals to x. Side OM equals to x. Side OM equals to x. In the next step, we'll focus at this point, that is the touching point between the circle and the quarter circle. And we define this touching point as point K. Repeat again, point K is the touching point between the circle and the quarter circle. That is to say, the circle and the quarter circle are touching each other internally. At point K, the circle and the quarter circle have an internal lunge between them. Repeat again, at point K, the circle and the quarter circle have an internal lunge between them. Okay, they are touching each other internally at point K, and whenever two circular shapes are touching each other internally, then the straight line that joins their centers together must pass through their touching point. That is to say, from point K. Okay? Whenever you have two circular shapes that have an internal lunge between them, like in our drawing, then the straight line that joins their centers together must pass through their touching point. In this case, it is point K. So here we know that point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is the straight line OP. And according to the rule that I mentioned, this straight line OP, must pass for point K, that is their touching point. Okay? Or if the straight line OP must pass for point K, it means that OPK is one straight line. Okay? Line segment OPK is one straight line. Okay, line segment OPK is one straight line. We can also say, in other words, that points O, P, and K, they are all located on the same straight line. So if OPK is one straight line, it means that OK is also a straight line. OK is a straight line. And derive from it that OK is a straight line. Okay, so we found out that OK is a straight line. What is the definition of the straight line OK? Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle that is equal to capital R according to our definition. So you can write down that OK equals to capital R, that is the radius of the quarter circle. Okay. So here, point P is the center of the circle. Point K is the point on the circle itself. This is exactly the definition of a radius. That is to say, PK is the radius of this circle that is equal to 2 units according to what is given as the question. So I can write down here that PK equals to 2 units. This is the radius of the circle. In conclusion, I found out that PK equals to 2 and OK equals to capital R, that is the radius of the quarter circle. And what is the length of line segment OP? What is the length of this line segment? What is the length of this line segment OP? Here, point from the drawing, it is very easy to see that the length of this line segment OP or PO equals to OK minus PK. Again, OK minus PK equals to OP. So OP equals to OK minus PK. Repeat again. The length of line segment OP equals to OK minus PK. So OP equals to OK, but OK equals to capital R, it is the radius of the cover circle, minus PK. PK equals to 2, it is the radius of the circle. So in conclusion, we found out that the length of line segment OP equals to capital R minus 2. So we can write here that OP equals to capital R minus 2. In the next step, I will copy the right triangle OPM in a new page, and we will implement the Pythagoras theorem on this right triangle OPM. Okay. We just right now found out that the hypotenuse OP equals to capital R minus 2. So this is triangle OPM that I copied from the original drawing. Now we will implement the Pythagoras theorem on this right triangle OPM. We know that OM equals to X, and PM is the radius of the circle that is equal to 2 units. So here I write down that by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, therefore the square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM squared minus PM squared. I'll repeat again. According to the Pythagoras theorem and equation number 1, OP squared equals to OM squared plus PM squared. So here OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared, and it is equal to OM squared. OM equals to X, therefore OM squared equals to X squared plus PM squared. PM equals to 2, therefore PM squared equals to 2 squared, that is 4. So in conclusion, we found out that R minus 2 squared equals to X squared plus 4 according to equation number 1. So here we will open the brackets on this side of equation number 1, and we will get that according to equation number 1, R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R. In the other side of the equation we have X squared plus 4. Here we have 4 on both sides of equation number 1, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4 what is left is actually, in this side of the equation we have x squared, and x squared equals to r squared minus 4r. So we actually found out that according to equation number 1, x squared equals to r squared minus 4r. Okay? In the next step, we will focus at this point. That is actually the touching point, or the point of tendency between the circle and the semicircle. Or, in other words, at this point, the semicircle and the circle have an external notch between them. So we define the touching point between the circle and the semicircle as point T. At point T, the circle and the semicircle have an external notch between them. And whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. I repeat again. Whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point, that is point T in this case. So here, according to the rule that I mentioned, here point P is the center of the circle, point Q is the center of the semicircle, and the straight line that joins their centers together is the straight line QP. And this straight line QP, must pass through point D, that is actually their touching point. So the straight line QP must pass through point T, that is their touching point. That is to say, if the straight line QP must pass through point T, it means that QTP is one straight line. So you can write down that here that line segment QTP is one straight line, instead of saying line segment QTP is one straight line, we can also say that points Q, T, and P, they are all located on the same straight line. Okay? Two different ways to say the same thing. Okay? So if QTP is a straight line, it means that QP is also a straight line. So here QP is a straight line. QP is a straight line. So what is the length of the straight line QP? From the drawing, it is very easy to see that the length of the straight line QP, it is equals to QT plus TP. QT plus TP. Okay? QP equals to QT plus TP. So QP equals to QT plus TP, and here point Q is the center of the semicircle, point T is the point of the semicircle itself. This is exactly the definition of a radius. That is to say QT is the radius of this semicircle, that is equal to 2 units according to what is given as the question. Likewise here, point P is the center of the circle, point T is the point of the circle itself. Therefore, PT is the radius of this circle, that is also equals to 2 units. So in conclusion, found out that QT equals to 2 and TP equals to 2. So here QT, it is equal to QP equals to QT plus TP, and QT equals to 2, and TP also equals to 2. So in conclusion, we found out that QP equals to 2 plus 2, that is 4. So we can write down that here that QP equals to 4. QP equals to 4 units. Okay. And write down here that QP equals to 4 units. In the next step, but what is the length of line segment BQ? Point Q is the center of the semicircle. Point B is the point of the semicircle itself. Therefore, QB is the radius of the semicircle, that is equal to 2 units. And what is the length of line segment QL? From the drawing, it is very easy to see that the length of line segment QL equals to BO, that is equal to capital R, minus BQ, that is equal to 2, minus LO. So QL equals to BO, that is the radius of the quarter circle, it is equal to capital R, minus BQ, that is the radius of the semicircle, that is equal to 2, minus LO, that is equal also to 2. I repeat again, the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So actually we found out that QL equals to BO, that is equal to capital R, it is the radius of the quarter circle, minus BQ, that is equal to 2, it is the radius of the semicircle, minus LO, that is equal to 2. So in conclusion, we found out that BQL equals to capital R minus 2 minus 2 minus 2 minus 2 is minus 4. So QL equals to capital R minus 4. QL equals to capital R minus 4. So I can write here that QL equals to capital R minus 4. Now I'll copy the right triangle QLP in a new page and we'll implement the Pythagoras theorem on this triangle, triangle QLP. Okay. So QL equals to capital R minus 4. LP equals to X, and the hypotenuse QP equals to 4 units. So this is triangle QLP that I copied from the original drawing. Now we will implement the Pythagoras theorem on this right triangle, triangle QLP. So here, by PT is the abbreviation for Pythagoras theorem. I according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to QL squared plus LP squared. Okay? According to equation number 2 and according to the Pythagoras theorem, we found out that QP squared equals to QL squared plus LP squared. QP equals to capital R minus 4, therefore QP squared equals to capital R minus 4 squared. And it is equal to Q here I made a mistake. QP, the hypotenuse QP equals to 4. Therefore, QP squared equals to 4 squared, that is 16. So QP squared equals to 16, and it is equal to QL squared. QL equals to capital R minus 4, therefore QL squared equals to capital R minus 4 squared plus LP squared. LP equals to X, therefore LP squared equals to X squared. So in conclusion, found out that according to equation number 2, 16 equals to capital R minus 4 squared plus X squared. Here we open the brackets on this side of equation number 2 and we get that according to equation number 2, Sixteen equals to R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus X squared. So here we have 16 on both sides of equation number 2, therefore 16 will get cancelled. And what is left from equation number 2 after we cancel 16? In this side of the equation nothing is left, so we have 0. In the other side of the equation we have R squared minus 8R plus X squared. So here we will add 8R to this equation, equation number 2, and we'll get that according to equation number 2, R equals to R squared plus X squared. So here we subtract R squared from this equation, equation number 2, and we'll get that according to equation number 2, X squared equals to 8R minus R squared. This is according to equation number 2, but according to equation number 1, we have already found out that X squared equals to R squared minus 4R. So here we have two different expressions for X squared. X squared equals to R squared minus 4R according to equation number 1, while X squared equals to 8R minus R squared according to equation number 2. Therefore, we create equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. So here X squared according to equation number 1 is equal to R squared minus 4R, and it must be equal to X squared according to equation number 2, that is equal to 8R minus R squared. So in conclusion, according to equation number 3, we found out that R squared minus 4R equals to 8R minus r squared. Here we will add r squared to this equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. So here we will add 4r to this equation number 3, and we get that according to equation number 3, 2r squared, 4r minus 4r is 0, and it is equal to 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we will divide this equation by 2, and we get that according to equation number 3, 2r squared over 2 is r squared. That is equals to 12r over 2 is 6r. So according to equation number 3, we found out that r squared equals to 6r. Here we subtract 6r from this equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. In the next step, we'll take a common factor r from these two expressions, and we'll get that. So here r is a common factor. What is left from r squared after we took from it r is a common factor. What is left is actually r. And what is left from minus 6r after we took from it r is a common factor. What is left is actually 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution for r is that r equals to 0. But because of the fact that r is the length of the radius of the quarter circle, so r as a length, it must be a positive number. It can never be equal to 0, so we cancel this solution, and we left only the second solution, that r minus 6 equals to 0. Here we will add 6 to this equation, and we get that r equals to 6 units. So we found out that the radius of the semicircle r equals to 6 units. Therefore, the area of the semicircle is equals to the radius of the quarter circle r equals to 6 units. Therefore, the area of the quarter circle will be equal to the radius of the circle over 4. That is to say, it will be equal to pi r squared over 4, and r equals to 6. And what is the area, the value of the shaded area? The value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay. I've already explained the area of the semicircle equals to the area of the circle over 4, that is pi r square over 4, and r equals to 6 units. Okay, so the area of the quarter circle equals to pi r square over 4 minus the area of the circle. The area of the circle is pi r square, and r equals to 2, so it is pi 2 square minus the area of the semicircle. The area of the semicircle equals to the area of the circle over 2, that is pi r square over 2, and r equals to 2, so it is pi 2 square over 2. So in conclusion, we found out that the value of the shaded area equals to this expression: pi r square over 4 is the area of the quarter circle minus the area of the circle, that is pi 2 square, minus the area of the semicircle, that is pi 2 square over 2. We have already found out that the radius of the quarter circle r equals to 6, so r square is 6 squared, that is 36. So in total this expression equals to 36 pi over 4. So I'll write it down. The area of the quarter circle equals to 36 pi over 4 minus the area of the circle is pi 2 square. 2 square is 4, and 4 times pi is 4 pi, so the area of the circle is 4 pi, so it is minus 4 pi minus pi 2 square over 4. 2 square is minus 2 square over 2, it is the area of the semicircle equals to the area of the circle over 2, and the area of the circle is pi 2 square, and when we divide it by 2, it will give us the area of the semicircle. So the area of the semicircle equals to pi 2 square over 2. 2 square is 4, and 4 over 2 is 2. 2 times pi is 2 pi. So in conclusion, the area of the semicircle equals to 2 pi. So it is minus 2 pi. So here we have 36 over 4 is 9, and 9 times pi is 9 pi. So in total this expression equals to 9 pi minus 4 pi minus 2 pi. So the value of the shaded area equals to 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So we actually found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay. I repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. We finished with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the drawing we have triangle ABC. Angle ABC equals to 30 degrees, angle ACB equals to 30 degrees, angle DAE equals to 60 degrees, line segment BD equals to 5 units, line segment EC equals to 4 units, and our mission is to find out the value of line segment DE that is equal to X. So first of all, we focus on triangle ABC. In triangle ABC, those two angles, they are equal to each other, they are both equal to 30 degrees. So in triangle ABC, we know that angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that side AB equals to side AC because those two sides are located in front of those two equal angles that they are equal to 30 degrees. So AB equals to AC, and we define this angle as beta and this angle is alpha, and we also know that the sum of the angles in any triangle, and especially in triangle ABC, must be equal to 180 degrees. So here we have 30 degrees plus 30 degrees plus beta plus 60 degrees plus alpha. In total, they must be equal to 180 degrees. So 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation, we have 180 degrees plus alpha plus beta, and the other side of the equation, we have 180 degrees. So we subtracted 120 degrees from this equation and we found out that alpha plus beta equals to 180 degrees minus 120 degrees equals to 60 degrees. So we found out that in conclusion that alpha plus beta equals to 60 degrees. Then we did two constructions. The first construction is that from point A we draw a straight line in such a way that the angle between the straight line and side AC will be equal to beta. And the second construction that we did is that from point C we draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. I repeat again that this angle equals to beta and this angle equals to 30 degrees according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of the two straight lines, of the two extended straight lines. So by doing this construction, we added here triangle AFC. Then the next step we proved that the new triangle AFC is congruent to this triangle ABD. Okay, so why those two triangles congruent to each other? First of all, those two angles are both equal to beta, therefore they are equal to each other. So here angle BAD, this angle equals to this angle that is actually angle CAF, and they are both equal to beta, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF, and they are both equal to beta, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC, so therefore side AB in triangle ABD is equal to side AC in triangle AFC. AB equals to AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So actually, angle ABD in triangle ABD equals to angle ACF in triangle ACF, and they are both equal to 30 degrees, therefore they are equal to each other. In conclusion, we found out that triangle ABD is congruent to triangle ACF according to angle side angle rule. To explain what I mean, here we actually proved that those two angles and the side that attached to those two angles in triangle ABD are corresponding congruent to those two angles and the side that attached to those two angles, that is side AC, in triangle AFC. Therefore, we proved that those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we conclude two things. The first thing that we will conclude that side BD in triangle ABD is equal to side FC in triangle AFC. Here, side BD equals to side FC. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given as the question, side BD equals to 5 units. So we can write here that BD equals to 5 units, and from this equation 5 equals to BD equals to FC, we will derive that side FC is also equals to 5 units. Here, side FC also equals to 5 units. And the second thing that we will conclude from the fact that those two triangles congruent to each other is that side AD equals to side AF. Side AD equals to side AF. According to the same rule, that corresponding sides in congruent triangles are equal to each other. And if we define side AD as A, then, so here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. Here side AF is also equals to A. In the next step, we join points E and F together by a straight line, and then we proved that the green triangle is congruent to the orange triangle. Why those two triangles congruent to each other? First of all, we just right now proved that those two angles are equal to each other, they are both equal to A, therefore they are equal to each other. Okay? Angle AD equals to angle AF equals to A. Okay? In addition, we already proved that alpha plus beta equals to 60 degrees. So those two angles, they are both equal to 60 degrees, therefore they are equal to each other. Okay, so here angle DAE in the green triangle equals to angle EAF in the orange triangle, and they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself. AE equals to AE is a common side that belongs to both triangles. So in conclusion, we actually proved that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF, according to a side angle side rule. I'll repeat again and explain what I mean actually. Here we proved actually that those two sides and the angle between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, we proved that those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other, we conclude that side DE equals to side EF according to the same rule that corresponding sides in congruent triangles are equal to each other. Here side DE in the green triangle is equal to side EF in the orange triangle. But according to what is given as the question, side DE equals to X. Side DE equals to X. So I can write here that DE equals to X, And from this equation, x equals to DE equals to EF, we derive that side EF is also equals to x. Here side EF also equals to x. Okay. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle, so you can write down here that in any triangle, this triangle ABC could be any triangle. The length of side AB is A units, the length of side AC is B units, and the angle between side AB and side AC is theta, and the length of side BC is C units. So this triangle ABC, the following equation is true, that C square equals to A square plus B square minus 2 times A times B times cosine theta. Repeat again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle EFC. So I copied triangle EFC here. Here this angle ECE, FCE equals to 30 degrees plus 30 degrees, this is 60 degrees. Side FC equals to 5 units, side EC equals to 4 units, and side FE equals to x, that is the line segment that we are looking for. So, according to the, if we implement the law of cosines in this triangle EFC, we will get that x square equals to 4 square plus 5 square minus 2 times 4 times 5 times cosine 60 degrees. Okay? So here x square equals to 4 square is 16 plus 5 square is 25 minus 2 times 4 is minus 8 and minus 8 times 5 is minus 40 and cosine 60 degrees equals to 1/2, so we substitute cosine 60 degrees by 1/2. So in total this expression equals to minus 40 times 1/2. Okay, so here 4 x square equals to 4 squares is 16, 5 squares is 25, and minus 2 times 4 is minus 8 times 5 is minus 40 times 1/2. And so we found out that x square equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x square equals to 41 minus 20. 41 minus 20 is 21, so in conclusion, we found out that x square equals to 21. We took a root out of this equation and found out that x equals to the positive square root of 21. In terms of numbers, it is equal to 4.58 units. I repeat again that because of the fact that x is a length, it must be a positive number. Therefore, we will take only the positive square root of 21. So the answer to the question is that line segment DE, this line segment DE, that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question. Then I presented to you the second question. In the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at point T. And we also know that this circle is tangent to the quarter circle at point K. And we know that the radii of both the circle and the semicircle is equal to 2 units. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, it means that this point O, must be the center of the quarter circle. this angle LOM must be equal to 90 degrees, and side OA must be the radius of the quarter circle, and side BO must be also the radius of the quarter circle. Those three things is always true for any quarter circle. Okay? And here we have the radius OA is tangent to the radius OA of the quarter circle is tangent to this circle at point M. Point M is the point of tendency of tangent OA with this circle. Point P is the center of the circle. Point M is a point on the circle itself, therefore PM is the radius of this circle that is equal to 2 units. And we also have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule number 1. Actually, you can implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, then from the center of this circle that is actually point P, we go perpendicular on QO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Okay, then we define the touching point of the perpendicular from point P and QO as L. Point L is the touching point of the perpendicular from point P and QO. So actually, by doing this construction, we created quadrilateral LPOM that has 1, 2, 3 right angles. Okay, I wrote it down here that in quadrilateral LPOM we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees plus the size of the fourth angle. In total, the sum of those 4 angles, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and found out that the missing angle LPM equals to 360 degrees minus 270 degrees is 90 degrees. So this angle is a right angle. This angle is a right angle. Actually, we found out that all the angles inside quadrilateral LPOM are right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM that has 4 right angles as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, rectangle LPOM, side PM must be equal to side LO. PM equals to LO, but we have already found out that PM equals to 2 units. This is the radius of the circle. So here we can write down that PM equals to 2, and from this equation 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side LP equals to side OM. LP equals to OM. So if we define side LP as X, here side LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that OM is also equals to X. Here OM is also equals to X. Okay, in the next step we focus at this point, that is the touching point between the circle and the quarter circle. We defined the touching point between this circle and the quarter circle as point K. Actually at point K, the circle and the quarter circle have an internal length between them. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that have an internal length between them, then the straight line that joins their centers together must pass through their touching point. I repeat again, whenever you have two circular shapes that have an internal length between them, then the straight line that joins their centers together must pass through their touching point. In this case, point O is the center of the quarter circle, point P is the center of the circle, and the straight line that joins their centers together is the straight line PO. And according to the rule that I mentioned, this straight line that joins their centers together, PO, must pass through their touching point, that is point K. Or the straight line OP must pass through point K. That is their touching point. Or in other words, you can say that OPK is one straight line. Because of the fact that the straight line OP must pass through point K, it means that OPK is one straight line. Okay, so here OPK is one straight line, or you can also say that points O, P and K, they are all located on the same straight line. Okay, so if OPK is a straight line, then OK is also a straight line. OK is a straight line, but what is the definition of OK? O is the center of the quarter circle. K is the point on the circle itself. K is the point on the quarter circle itself. Again, point O is the center of the quarter circle. Point K is the point on the quarter circle itself. That is to say, OK is the radius of the quarter circle that is equal to capital R according to our definition. So you can write down that OK equals to capital R, it is the radius of the quarter circle. Point P is the center of the circle. Point K is the point of the circle itself. This is exactly the definition of a radius. That is to say, PK is the radius of this circle that is equal to 2 units. So you can also write that PK equals to 2 units. So you conclude and found out that OK equals to R and PK equals to 2. And what is the length of line segment OP? The length of line segment OP equals to OK minus PK. Again, OP equals to OK minus PK. Repeat again. OP equals to OK minus PK. So OP equals to OK, that is equal to capital R, it is the radius of the quarter circle, minus PK, that is equal to 2, it is the radius of the circle. So in conclusion, I found out that the length of line segment OP is capital R minus 2. Here OP equals to capital R minus 2, then I copied the right triangle OPM in a new page and we implemented the Pythagoras theorem on this right triangle, triangle OPM. So this is the right triangle OPM that I copied from the original drawing. We just right now found out that the hypotenuse OP equals to capital R minus 2, PM equals to 2 units, it is the radius of the circle, and OM equals to X. Okay, and this again equals to 90 degrees according to our construction. So we implemented the Pythagoras theorem on the right triangle in OPM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is OP square. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM square plus PM square. So OP is capital R minus 2, therefore OP square is capital R minus 2 square, and it must be equal to OM square. OM is X, so OM square is X square. plus PM squared. PM is 2, so PM squared is 2 squared, that is 4. So in conclusion, found out that according to equation number 1, r minus 2 squared equals to x squared plus 4. So here we open the brackets on this side of equation number 1. So r minus 2 squared equals to r squared plus 2 squared, that is 4, minus 2 times r times 2 is minus 4r. And in the other side of the equation we have x squared plus 4. So we have 4 on both sides of equation number 1, so 4 we get cancelled, and we left only with x squared, that is equal to r squared minus 4r. So according to equation number 1, we found out that x squared equals to r squared minus 4r. Then we focused at point T, that is the touching point between the circle and the semicircle. Actually, at point T, the circle and the semicircle have an external length between them. That is to say, they are touching each other externally at point T. And whenever you have two circular shapes that have an external length between them, then the straight line that joins their centers together must pass through their touching point. I repeat again, whenever you have two circular shapes that have an external length between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point T. So here point P is the center of the circle, point Q is the center of the semicircle, and the straight line that joins their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP must pass through point T, that is their touching point. Or in other words, we can say that points Q, T, and P, they are all located on the same straight line, or QTP is one straight line. Okay, here QTP is one straight line, or points QT and P, they are all located on the same straight line. So if QTP is a straight line, then QP is also a straight line. So we found out that QP is a straight line, and what is the length of the straight line QP? The length, it is very easy to see from the drawing that the length of the straight line QP equals to QT plus TP. Again, QP equals to QT plus TP. Here, QP equals to QT plus TP. What is the length of QT? Point Q is the center of the semicircle. Point T is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, QT is the radius of this semicircle, that is equal to 2 units. Okay, so we found out that QT equals to 2 units. Likewise, point P is the center of the circle. Point T is the point on the circle itself. That is to say, TP is the radius of this circle, that is equal to 2 units. So in conclusion, we found out that QT equals to 2 units and TP equals to 2 units. So here we can write down that QT equals to 2 units and TP equals to 2 units, and QP equals to QT, that is 2, plus TP, that is also 2. So in conclusion, we found out that QP equals to 2 plus 2, that is 4. So here QP, the straight line QP equals to 4 units. Then we found out the value of line segment PQ. What is the value of line segment PQ? Point Q is the center of the semicircle. Point B is the point of the semicircle itself. Therefore, BQ is the radius of this semicircle, that is equal to 2 units. Then we found out the length of line segment QL. What is the length of line segment QL? It is very easy to see from the drawing that the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. Again, QL equals to BO minus BQ minus LO. Okay, repeat again. QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So here, QL equals to BO that is equal to capital R minus BQ that is equal to 2 units minus LO that is equal to 2 units also. So in conclusion, we found out that QL equals to capital R minus 2 minus 2. So minus 2 minus 2 is minus 4. So in conclusion, we found out that QL equals to capital R minus 4. Here QL equals to capital R minus 4. Then I copied the right triangle QLP in a new page and we implemented the Pythagoras theorem on this right triangle QLP. So this is the right triangle QLP that I copied from the original drawing. We have already found out that the hypotenuse QP equals to 4 units. LP side LP equals to X. And we just right now found out that Qn equals to capital R minus 4. This angle equals to 90 degrees according to our construction. So we implemented the Pythagoras theorem on this right triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared. It must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QL squared plus LP squared. So QP equals to 4, therefore QP squared is 4 squared, that is 16. And it must be equal to QL squared. QL is capital R minus 4, therefore QL squared is capital R minus 4 squared. Plus LP squared. LP equals to X, therefore LP squared equals to X squared. So in conclusion, we found out that according to equation number 2, 16 equals to capital R minus 4 squared plus X squared. We open the brackets on this side of the equation and we found out that 16 equals to capital R minus 4 equals to capital R squared plus 4 squared, that is 16, minus 2 times capital R times 4, that is minus 8R plus X squared. Here we have 16 on both sides of equation number 2, so 16 will get cancelled. What is left from equation number 2 after we cancel 16? What is left here is that in this side of the equation nothing is left, we have 0. In the other side of the equation we have R squared minus 8R plus X squared. So here we added 8R to this equation number 2, and we found out that according to equation number 2, 8R equals to R squared plus X squared. Here we subtracted R squared from this equation number 2 and found out in conclusion that according to equation number 2, X squared equals to 8R minus R squared. So we have two different expressions for X squared. According to equation number 2, X squared equals to 8R minus R squared, while according to equation number 1, X squared equals to R squared minus 4R. Therefore, we created equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. X squared according to equation number 1 equals to R squared minus 4R, and it must be equal to X squared according to equation number 2, that is equal to 8R minus R squared. So here we added R squared to this equation number 3, and found out that R squared plus R squared is 2R squared. So in this side of the equation we have 2R squared minus 4R. In the other side of the equation, what is left, it is actually 8R. So in conclusion, according to equation number 3, we found out that 2R squared minus 4R equals to 8R. Here we added 4R to this equation number 3, and we found out that 2R squared, 4R minus 4R is 0, so 2R squared equals to 8R plus 4R is 12R. So 2R squared equals to 12R. According to equation number 3, we divided equation number 3 by 2, and we found out that R squared, 2R squared over 2 is R squared, and 12R over 2 is 6R. So in conclusion, we found out that according to equation number 3, R squared equals to 6R. We subtracted 6R from this equation number 3, and found out that R squared minus 6R equals to 0. Here we took a common factor of capital R from these two expressions. What is left from R squared after we took from it R is a common factor. What is left is actually R, and what is left from minus 6R after we took from it R is a common factor. What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, R times R minus 6 equals to 0. So here we will have two solutions that are possible for R. either r equals to 0, and the second solution is that r minus 6 equals to 0. But r can never be equal to 0 because r is the length of the radius of the quarter circle, and it must be a positive number. So we cancel this solution that r equals to 0, and we left only with the second solution that r minus 6 equals to 0. We added 6 to this equation. We found out that the radius of the quarter circle equals to 6 units. Therefore, the area of the quarter circle will be equal to the radius of the circle over 4, that is pi r squared over 4, when r equals to 6. And what is the value of the shaded area? The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the value of the shaded area equals to the area of the quarter circle, that is pi r squared. Again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the value of the shaded area equals to the area of the quarter circle, that is pi r squared over 4, minus the area of the circle, that is pi r squared, and r equals to 2, so it is pi 2 squared, minus the area of the semicircle, that is pi r squared over 2. And r equals to 2, so it is pi 2 squared over 2. The area of the circle and the quarter circle is pi r squared over 2, and r equals to 6, so the area of the quarter circle is 36 pi over 4, minus the area of the circle, that is pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi, so the area of the circle is 4 pi, minus the area of the semicircle, that is pi 2 squared over 2, that is 2 pi. 36 over 4 is 9, so this expression equals to 9 pi. So we actually found out that the area of the value of the shaded area equals to 9 pi minus 4 pi, that is 3 pi, and 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.